We have developed an indigestible, swallowable, gas-sensing capsule that can send data of the gas constituents in the gastrointestinal tract to handheld devices. The microbial consortia of the gastrointestinal tract has been shown to contribute to overall state of health, development, and metabolic needs. Their community structure and functionality are associated with our genetics, specific dietary patterns, stress and disease, as well as any environmental effects. As such, the gas constituents of our gastrointestinal tract can be used as invaluable biomarkers for identifying our state of health. Some examples of the effects and disorders that can be supposedly identified from the gas profiles are as follows. Excess gas production can cause pain and discomfort. Hydrogen and methane are biomarkers that can be used for characterizing carbohydrate malabsorption within patients. Methane itself is an acidic gas that has been associated with disruptions in peristaltic activity. In addition, the production of methane has been strongly correlated with constipation-type irritable bowel syndrome. Hydrogen sulfide is a gasotransmitter that plays important roles in chloride secretion in the gastrointestinal tract. The presence of hydrogen sulfide is associated with damaged intestinal epithelium and may be linked with inflammatory bowel disease and colon cancer. Nitric oxide is another gasotransmitter which contributes to the regulation of intestinal motility, mucosal blood flow, and secretory functions. This has also been considered as a marker for inflammatory bowel disease. Currently, the most common non-invasive method for assessing gastrointestinal tract gas constituents have been based on breath analysis. However, they don't provide a correct representation of intestinal gases due to the interferences from the passage in the bloodstream to the lungs and the contaminants in the mouth. Alternatively, measurement of gas production from fecal microbiota is a convenient approach. Nevertheless, these gases are only a reflection of production within the distal colon and rectum. Furthermore, all other methods of analyzing intestinal gases, such as inserting tubes into the body, are shown to be invasive and inconvenient. Therefore, these capsules can potentially play an important role in assessing the state of human health as a real-time diagnostic tool. We ourselves have developed the gas capsules that are used in the presented experiments, where each capsule is comprised of a gas sensor based on thermal conductivity, which is sensitive to carbon dioxide, hydrogen, and methane. It contains a polymer-based membrane at the front of the sensor made of rubbery polydimethylsiloxane with embedded nanoparticles to increase its permeability to the target gas molecules but not gut luminal liquid. Within its small 12 by 35 mm housing, the capsule contains a high-capacity, non-hazardous power supply, a microcontroller, and a wireless transmitter operating at 433 MHz and a spiral antenna. These elements obtain, convert, and process gas sensor outputs and subsequently communicate the data to a light handheld external receiver. The gas data is sent out every 5 minutes, and between transmissions, the system goes into sleep mode to increase battery lifetime. We show the validity and operation of these capsules by presenting the outcomes of model experiments on pigs of high and low fiber diets. The pig's gastrointestinal tract has a microbial ecosystem that is comparable to the human gut microbiome, making it an ideal model for the human gastrointestinal tract. The gas capsule operation was benchmarked against classical measurements by Jensen and Johansen from 1994 on pigs fed with high and low fiber diets. In these old experiments, the gas constituents of selected segments of the gastrointestinal tract of the pigs on high and low fiber diets were immediately extracted from the headspace after they were slaughtered and measured using a gas chromatography system. In our experiments, the 4-month-old pigs were kept in crates during the capsule measurements. 2 pigs on a high fiber diet and 2 pigs on a low fiber diet to emulate Jensen and Johansen's experiments. The pigs were fed twice a day for each set of measurements. 1 feed immediately after the capsule was gavaged and once in the late afternoon. The gut microbiota of the pigs was first acclimatized to a human-type diet for a week to reach a baseline. They were then randomly allocated to receive 2 types of diets with either high or low fermentable carbohydrate contents for 4 days each. Fermentable carbohydrate composition in the high and low diets comprised of 60 grams versus 9 grams resistant starch and 45 grams versus 3 grams of fructo and galacto oligosaccharides respectively, and the diets were otherwise matched in other macronutrients. The results from our pig trials on the high and low fiber diets are as follows. After each feeding, there were drops in the signal due to excess of nitrogen and oxygen trapped in the food entering the gastrointestinal tract. The baselines, however, were regained soon after, and drinking water alone did not affect the signal. Pigs on a high-fiber diet showed an increase in carbon dioxide throughout the experiment, while those on a low-fiber diet did not show any change in carbon dioxide profile with reference to the baseline. The capsule operated between 10 and 30 hours, and those that passed the 15-hour mark reached the cecum. Interestingly, from our experiments exceeding 20 hours, significant troughs can be seen that don't relate to feeding times. These occur between 11 and 15 hours, which is likely the time that the capsule takes to reach the jejunum and represent the presence of hydrogen. With the low-fiber diet producing approximately 4 to 5 times the hydrogen concentration as the high-fiber diet, which is the same ratio that Jensen and Johansen obtained from their in vitro sampling. After reaching the cecum, gas profiles of both diets reached the 60% mark for carbon dioxide, which is similar to that shown by Jensen and Johansen. In total, it took up to 2 weeks for the capsules to be passed by the pigs. The issues that are yet to be addressed include enhancing the lifetime and improving transmission reliability of these capsules, assuring that no capsule retention occurs by high-quality manufacturing, reducing the size of the capsules, and improving the hydrodynamics. The inclusion of one or more gas or vapor sensor to allow simultaneous measurements of biologically important gas species. An eventual exploration into the relationship between intestinal gas constituents, gut microorganisms, and the health status. And finally, to establish libraries based on different health status and gas constituents is still needed. To conclude, we demonstrated successful operation of gas sensing capsules using a pig model on high and low fiber diets. The carbon dioxide and hydrogen profiles were obtained, and observations were mostly in agreement with the classic work by Jensen and Johansen, which demonstrate the correct operation of the capsules under different diets. As such, the novel capsule system can be potentially used as a non-invasive and reliable human gastrointestinal tract health assessment unit.